Okay, so we're going to do rational graphs. There are two different types of ways we can make these, and we talked about this today. The transformed form, remember how you'll set it up, is there'll be y equals a. Either way, both forms are going to need an a. And then you end up with the vertical asymptote factor down here. And then if there's a point of discontinuity, it also ends up down here, which means it ends up top. Now, if there isn't a point of discontinuity, we just completely don't put these two brackets. And then at the back, you have the horizontal asymptote. Remember? And you'll need to use a point to solve for a. So that's the transformed form. And then the full fraction form we talked about the other day, where we do y equals a x-intercept, point of discontinuity if there is one, in the numerator. And then in the bottom, we have vertical asymptote and a p of d if there is one. And then we use a coordinate and solve for a value. So those are the two. And sometimes transformed form is better, sometimes full fraction is better. And then when you're doing the one where the numerator is bigger than the denominator, which is the last one, full fraction is the way to go. So transformed form, let's look at this one first. So we're going to get y equals a. And then if there's a point of discontinuity, it goes to the top. There is one. It's at x equals -2. So the factor is going to be x plus 2. And it's going to appear in the numerator and the denominator. Also in the denominator is the one that doesn't cancel off, which is the vertical asymptote, which is right here. And it's at x equals 1. So my factor is going to be x minus 1. And then in transformed form, we get our horizontal asymptote at the end, which is at y equals, this should be a y, it kind of looks like it's an x, but it's not. Y equals 1. So we add a 1 in the back. Now we need to use a coordinate to solve for a. But remember, sorry, I had to cough. But remember, when we go to solve for a, we actually use the simplified form, because if we kept those points discontinuity in there, sometimes they cause problems. So I'm going to use the y-intercept because it's bolded and the coordinates there. So it's at 0 and -3. And I'm going to plug it into the simplified one. So that's a over x minus 1 plus 1, and I'm going to solve for the a. So I'm going to get -3 equals a, 0 minus 1 plus 1. Subtract my 1 over. And I get -4 equals a over -1, multiplied by -1. And I get a equals 4, and I need to rewrite my equation. So we get y equals 4 x plus 2 all over x minus 1 x plus 2 plus 1. And we can leave it like this unless they have it in an expanded form. But the cool thing about the equations of rationals is if you type it into your calculator, you should get the rational graph that's in front of you. If you don't, you messed up. So that's how we do the transformed form. Full fraction, we do y equals a, and then x-intercept. So my x-intercept here is at -3, 0. So I'm going to get x plus 3. And then my point of discontinuity, which is x plus 2, because it's at -2. And then my vertical asymptote again, so I get x minus 1. And then my point of discontinuity, x plus 2. And I still have to solve for my a. So I'm going to use that same 0 and -3. And I'm going to put that in for x and 1. So I'm going to get -3 equals, into the simplified one, a 0 plus 3 over 0 minus 1. I'm not going to use the one with point of discontinuity, because those factors can cancel off. And then I'm going to multiply by -1. Get it off the denominator. So I get 3 equals a times 3, divided by 3. And a equals 1. So I don't actually have to, a doesn't always equal 1. It's going to be the next few examples for the full fraction, but it doesn't always, so we always have to check. So we get y equals 1, x plus 3, x plus 2, over full form, so they might FOIL it together and collect my terms. And we don't absolutely need the one, I'm just putting it there to point. So this is a rational function with a point of discontinuity. Well, what if they give me just a rational and no point of discontinuity, which is this one here? Still follows the same format. Transformed form is y equals a over vertical asymptote. My vertical asymptote is at x equals 1. So my factor is going to be x minus 1 down here. I don't have any more factors because I don't have a point of discontinuity. If I did have a point of discontinuity beside the a and beside the x minus 1, I'd get the same factor. And then at the back, I get my horizontal asymptote, which is at y equals 2. So I get a plus 2 back here. Now I need to use a coordinate. I'm going to use 0, 1. Solve for a. So I'm going to get 1 equals a over 0 minus 1 plus 2. Subtract my 2 from both sides. I'm going to get negative 1 equals a over negative 1 multiplied by negative 1. And a equals 1 here. Now remember, when we get our a, we still have to plug it back into the original. So we get y equals 1 over x minus 1 plus 2. And now remember, we should be able to type these into our calculators and get the graph that's in front of us. So we know if we're right or we're not with these. Just like solving, where you can find out where they intersect and you know if you're right or not. Graph, same thing. When you get an equation, you plug it back in. And if it matches the equation, or the graph, sorry, then the equation is correct. Full fraction, we do y equals a x-intercept over vertical asymptote, which is x minus 1. Now we need to get the x-intercept in factored form. Now if this was a test, they'd actually have to bold this and label it because it's kind of in the middle, because this is at 1/2 and 0. So let's work that back to a factor. So we have x equals 1/2. Now some people say, oh, that's x minus 1/2. Remember, we can't do that. We have to work it back in steps so that we don't have a fraction sitting there. So I multiply by the 2, and I get 2x equals 1, and then I subtract 1, and I get 2x minus 1 equals 0. So that's what's going to go in for my x-intercept. So I'm going to use the same coordinate, 0, 1. To solve for my a, to solve for my vertical stretch. So I'm going to get 1 equals a, 2 times 0 minus 1 over 0 minus 1. 1 equals a over negative 1 times negative 1 over negative 1. Negative 1 over negative 1 just cancels. So I actually am left with a equals 1. Like I said, these all end up in a equals 1, the full fractions, but it's not always that case. You have to check for vertical stretch. So I can write the 1 or not write the 1. It doesn't matter. And I can show the brackets or not. So if I type this one and this one into my calculator, remember making a thicker line on this one, they'll draw one on top of the other and they will match this graph, so we know we're good. The only one I would hazard you not to do the transformed form for is these ones where it's just a line with an open dot. Remember I told you when this happens, your numerator is a larger degree than your denominator, right? And so we're always going to use a full fraction when it's a line like this. So we get y equals a, x-intercept. My x-intercept is at negative 1, so I'm going to get x plus 1. And then I don't have any asymptotes. I only have a point of discontinuity, and it's at x equals 1. So I'm going to get an x minus 1 in the top and an x minus 1 in the bottom. And then I'm going to use the coordinate 0, 1 as my x, y. And remember, we always plug it into our simplified one. So our simplified one is the one without the point of discontinuity factors because they can cancel off. So I get 1 equals a 0 plus 1. So 1 equals a times 1. So once again, it is 1. And like I told you, you just always have to check to see if it is. So we're going to get y equals 1, x plus 1, x minus 1 over x minus 1. And we can leave it like this, but they might ask for it in the actual form together. So you get x squared plus x minus x cancels minus 1 over x minus 1. So this might be what you actually are given as a multiple choice answer. And that's the different ways that you can come up with the equations of the graphs. This is the only one that I would for sure do in a full fraction, because it doesn't make sense in the transformed. That's it.